Hello, this is Frank with Frank's Beautiful Rocks and Minerals. I want to talk about Bowens reaction series, and this time use examples. Let's get to the video. Oh, almost dropping equipment. Don't want to drop equipment. In volcanoes, whether active or inactive, times past, what happens in a volcano is underneath the earth is the mantle. The mantle is rich in magnesium and potassium, silicon and oxygen. Volcanoes take liquid rock that is heated by the mantle and enters the asthenosphere underneath the crust or lithosphere of the earth and starts to, by means of a tube or a vent, rise up to the surface of the earth. This occurs in different situations on Earth, at subduction zones, where the oceanic plate subducts underneath the continental plate, which is less dense, solid rock of the oceanic crust being 6 to 10 miles in depth, or 15 kilometers, melts in the asthenosphere and sends up in a pipe and into a magma chamber hot rock from the upper mantle into the asthenosphere and up to the surface, the lithosphere of the earth. The volcano could be of various types. Other volcanoes occur at seafloor spreading areas, where the seafloor spreads apart in a process called continental drift and causes a line of volcanoes because lava enters into the spreading seafloor, which is very thin and becomes volcanic, such as around the Pacific Ocean, the I can't think of it. What do you call it? The Ring of Fire. The Ring of Fire, a series of volcanoes, and also transverse faults causing earthquakes. And the other region of volcanoes or volcanism is in hotspots on continents, where underneath the earth is a hot spot, a magma plume rising up to the surface into the asthenosphere, bringing hot molten magma with it. Magma is liquid rock underneath the surface of the earth. Once it reaches the top of the earth and spews out of a volcano, it becomes lava. I have some examples of lava. This is vesicular basalt. This is basalt. It is low in silica content and therefore in the form of pahoehoe, as it's known, a Hawaiian word. It's slow flowing because it is not viscous. Why? It's not high in silica content. Rhyolite and dacite are types of magma high in silica content, high in viscosity, and become eruptive and explosive in volcanic eruptions. This is scoria, another type of volcanic rock. You'll notice, like with the basalt, the vesicles. The vesicles are regions of escaped gas. These are extrusive forms of lava once they solidify. some magma solidifies underneath a volcano and becomes specimens such as potassium felspar or orthoclase granite. The pink color here is the orthoclase. This one has muscovite mica on it. I prospected that. Other examples are, as I have in my collection, obsidian or volcanic glass erupted from explosive high felsic volcanoes where these obsidian fragments are spewed out and gas has no time to escape, so they solidify concordally immediately, forming what is commonly called volcanic glass. They also come in brown and a dark brown and a dark green. This is black. I have a lot of obsidian that's black. It's viscous, it's vitreous and adamantine, which means shiny on the surface. It is conchoidal, which means that it fractures like glass. You'll notice it looks like glass, the way glass breaks. But what are the two types of minerals or elements in minerals that are erupted from underneath the magma, brought up deep from the mantle into the asthenosphere, the liquid rock or magma underneath the asthenosphere, underneath the lithosphere or crust? Let's take a look at Bowens reaction series. Bowens reaction series. You'll notice that on this diagram, that on the left is temperature in Celsius. Starting at 1,400 degrees Celsius and decreasing to 800 degrees Celsius. As this temperature decreases, certain minerals, because of the melting point and solidification point of the elements that are contained in the minerals, will solidify out in the magma, in the lava rocks. There are two branches, the discontinuous branch, which is high in iron, magnesium, and potassium, and the continuous branch, the branch that brings up deep from underneath the surface high amounts of silica, oxygen, and potassium. Let's look at these two branches. Examples of minerals are given on each side. We start with mafic. We actually start with ultramafic, intermediate, and then felsic. So, in ultramafic minerals, the most ultramafic mineral is peridot. A lot of people call it peridot. Crystals I've prospected from Canada. They are conchoidal, transparent, green. Ultramafic rocks tend to be green. Once you get into the mafic series, they tend to be green and brown. The first one that we see that precipitates out will be the peridot. You may say peridot, I like saying peridot. The second one is olivine, and as you can see, as with the peridot, the olivine is green crystals. Then other ultramafic rocks start solidifying out at those high temperatures as they decrease in temperature. This is epidote. It is green. This is dunite. It is also, like the ultramafics, a green rock. So we see that as the temperature decreases, First the peridot, then the olivine, then the pyroxene, and the amphibole, as temperature decreases, solidify out until we get to biotite mica. Here's an example of biotite mica. This is a schist that I've prospected. Biotite mica, it's absolutely beautiful. And then the two branches combine. On the discontinuous high ultramafic branch, we know we have magnetite, rich in iron, another metal, hematite, and this is a purified, you can't call it a specimen now because it's purified by a laboratory. You have to call it a sample of magnesium. Okay, here we go. Magnesium metal. Magnesium metal is a very interesting metal. It's perfectly safe to handle. However, it has a unique quality about it, and that unique quality is the fact that magnesium metal will burn in a flame. There we go. There we go. Magnesium metal. What a unique property. Continuing. Then we go over into the Felsic branch of the continuous branch of Bowens reaction series. Silica and oxygen are high in the continuous branch and calcium rich. These are Felsic. This is omitted in the diagram. Now we're dealing with Felsic. The first mineral to solidify out as the temperature decreases is plagioclase felspar. Believe it or not, I do not have a representative specimen of plagioclase felspar yet. But it's actually easy to obtain. It's found as an ornamental stone in buildings, building facades, used alongside such things as granite, polished granite for walls. Sodium rich. Orthoclase. Here's a specimen of orthoclase. It's potassium felspar. Notice its crystalline structure around 90 degrees. Muscovite mica then precipitates out and solidifies at lower temperatures. This is a book of muscovite mica. It has basal cleavage, or 1 degree of cleavage. It's a very beautiful mineral. And then we have quartz. Here's a specimen of perfect cleavage, octahedral. Octahedral? No, octahedral's like fluorite. It's an octahedron. This is a specimen of clear quartz. It's has 6 sides to it, with a six sides capital or termination. This was prospected I prospected this at the Sterling Hill mine. Fractured on one side. This is not cut by lapidary. Hexagonal crystal form. It has no cleavage. Its breakage is conchoidal, meaning like it breaks like glass, but over time it will solidify into a crystal form. And that's where we end with the quartz. The last to solidify at 800 degrees Celsius, right under muscovite. Now, the continuous branch is rich in sodium. I have a specimen of sodium which I wish to show you. I have pure sodium metal. Pure sodium metal has a very interesting and unique property. You can handle it by your hands. It is a metal. It is therefore metallic. Let me get a paper towel. I store my sodium metal, which is an element. It is part of the first family on the periodic table of the alkali metals. It is related to hydrogen and potassium.